This is an example problem for Physics 1000, summer of 2013 at Auburn University. This is a very basic Coulomb force problem. We're given two charges that are Q1 and Q2 situated at a distance d from each other, and we're asked to find the force, the Coulomb force on one of these charges, and we'll find the magnitude and the direction. Now we're going to make this reasonably simplified because if you'll notice, the direction of the force kind of depends on which charge you're looking at. We know instinctively that positive and negative charges attract. So you have a positive charge here and a negative charge here. So we know that these are going to want to come together, but depending on your perspective tells you which direction the force is acting. If you're sort of riding along with Q1 here, you feel an attraction that's going to pull you this way. And if you're riding along with Q2, you see an attraction that's going to pull you this way. So what direction the force is applied depends on which particle you're quote-unquote riding along with. That's kind of a simplification. But for our purposes in this course, we're going to make this a little more simple, and we're going to assume that Q1 here is glued down. That is to say, it cannot move. And so we're only going to look at the force that's being applied to Q2. So how do we do that? Well, number one, you can probably guess the direction of this force just from symmetry. Or not symmetry, but geometry. So if we're looking at the force on Q2, it's going to be attracted to Q1, so that force is going to be directed this way. That makes sense, right? So all we're really left, the task is to find the magnitude. So because we're looking for a magnitude, we've already found our direction. We can ignore, at least for the present, this negative sign right here. Because the magnitude, remember, just means absolute value. So if I'm just looking for the magnitude of that force, I can take the absolute value and forget about the negative sign. I've already come up with a direction. I should say that the negative sign will tell you a direction, but in this case, we'll just ignore it and find the magnitude because we found the direction another way. So how do we do that? Well, we apply what we've learned about the definition of the Coulomb force, or how you calculate it. If you remember from class, it's just equal to the constant K times the product of the charges divided by the distance between them squared. So I found my direction. Now all I have to do is plug in numbers. Notice I'm using an R here for direction. That's pretty standard in these problems. Over here I have named it D, but don't let that fool you. It's just a distance. I said a direction. I meant a distance. It's just a distance. We've just given it two names. So let me start plugging in numbers. Your textbook gives you the value of K as 9 times 10 to the 9th newtons times meters squared over coulombs squared. That's 9 billion newtons times meters squared over coulombs squared. The units are kind of strange there. We'll see why they work in just one second. And then over here I've got, what do I have? 2C and a minus 3C. So I've got 2 coulombs. And remember, I'm ignoring the negative sign because I'm just looking for the magnitude, and 3 coulombs over my distance, which is 10,000 meters, 10 kilometers, which you might think is a very large distance, and it is, but it actually works out pretty well because I should point out 2 coulombs and 3 coulombs are actually pretty large charges. In the typical world, we find things that are charged in units of microcoulombs or millicoulombs, really sort of small charges. 2 coulombs and 3 coulombs is a pretty big set of charges there. So we still should expect to find a good amount of force 10,000 meters away. So let's see what happens. First of all, let's make sure we've written down everything correctly, and the way I like to do that is make sure my units work out. So I'm looking for a force, right, which has units of newtons. So look, there's my newton, so I have faith that I'm on the right track. But I only should have a newton, so I should expect all these other units to cancel out. Oh, and I missed one thing. This is the distance squared. So, I have a meter squared and a coulomb, meter squared over coulomb squared here that I should expect to go away because I just need a Newton. So let's look over here and look, I'm going to get a coulomb squared here and I'm going to get a meter squared down here. Coulomb squared over meter squared times the meter squared over coulomb squared is just going to give me 1. Sure enough, everything goes away except the Newton, so I feel confident that I've written down everything correctly. Now I can just plug this stuff into my calculator, and if you do that, you're going to come up with 540 newtons, which is a pretty sizable force for being 10 kilometers away. That's a pretty good distance, which tells you that 2 coulombs and 3 coulombs are actually pretty big charges. Also, this number here, the K, the constant K, is huge, 9 billion newtons times meter squared over coulomb squared. That's a very large number, which should tell you that the Coulomb force is actually a very, very strong force. It's not the strongest force we know of in nature, but it's a lot stronger than gravity, and you have some homework problems to illustrate that. But if anyone ever asks you which is the stronger force, electrical force or Coulomb or gravitational force, you should be able to answer pretty easily the Coulomb force. Okay, see y'all next time.